Okay, so last class we discussed about uh, how to solve Laplace equations using numerical methods. Okay. So how to solve Laplace equations? Any ideas? How we solved Laplace equations? Like what is Laplace equation? Del to u is 0. Grad to u equal to 0. That is dou to u by dou x2 plus dou to u by dou y2 equal to 0. So u is a function of both x and y. So instead of solving this analytically, we are solving this over a region. Uxy means this x and y belongs to some region R. Okay. How that region will be? It can be any smooth region. It can be any smooth region. Usually what we do, we approximate this smooth region as a grid. And the points on the region, various points on the boundary will be given to you, and your job would be to calculate based on these boundary values what are the points here. Okay, what are the points inside the boundary or inside this region? So using numerical methods we usually find this. And last class we saw that you can use standard 5-point formula, diagonal 5-point formula to compute all this. Moreover, like those are the methods. However, you can use the what do you call that? Like Gauss-Seidel and Jacobi method. Jacobi method you can use, and Gauss-Seidel method you can use. Gauss-Seidel will be more accurate than Jacobi. That much we have learned, and we have given one assignment to you. So I have seen most of the assignments, like how I did in last class. Many of them have not done it. Okay, so it is just a basic common sense. It is just basic common sense that if you are given this 1000, 2000 all values in the boundary, okay, these are your points. Okay, now what I suggested that we don't have these values u1, u2, u3, u4. So how are we going to find those values u1, u2, u3, u4? You can use diagonal 5-point. You can use standard formula for that. For finding this point, you can use this, and what? Like you can use this. Fine. It's totally fine. Or you can use the diagonal also. You can use these diagonal points also. Here, these boundary points also. Last class I have solved it. But most of you have taken it 0. Most of you have taken the initial condition as 0. But that is how you can take it 0. See, why I told you, you think in a very intuitive way. Think as an intuitive way that the temperature here is 1000 degrees Celsius. Temperature here is 2000 degrees Celsius. Okay. Suppose temperature here is 2000 degrees Celsius. If it is 2000 degrees Celsius here, how can it be 0 degree here? How can it be 0 degree there? How and all of them are 0 degree. Suppose you are taking that initial condition, right? So does it make sense? 2000, it is 2000 here and it is 500 here, and in between it is 0. Have you seen a metal like that? Have you seen a metal which is 2000 degree here, 500 degrees here, and 0 degrees here? Cannot be. Okay. So therefore, like last time I could have taken initial condition as my wish, right? I could have taken initial condition something 200, 300, 500, 400 and solved it, but I did not. What I did, I used those boundary values. I used the values which were given to me. You should take advantage of the boundary values being given to you. Yes. Hmm? What should we do? Yeah. Okay. So many of you have done. So what some other students have done is they have not taken zero. They have not taken zero. Rather than they have taken something else. Okay, 500. Let us take each of them 500. So you will get answer closer to the correct one, but you won't still get the correct answer. So what I suggest is these values are given to you. These values are given to you. So there is no essence in taking all this as zeros. There is no essence in taking all of this as zeros. I had solved this problem, right? See how I solved this. This is the first iteration I did. I took the values, I used all these values in the boundary and solved it. I never took this as initial guess as zeros. Hmm? So I hope that is clear. Hmm? So whenever you get this kind of problem, you should not take it directly zero. Okay. I hope you know why taking zero can be troublesome. You got the idea? How many of you got the idea? Why taking zero can be troublesome? If you take zero, in next iteration also you will get zero at some point. Some value you might, for other one it is coming. So anyway, so I hope that is clear. Hmm? So then what we did, we came across solving a parabolic PD, a parabolic PD. Okay. Previously what we did, we solved Laplace equation. Okay, Laplace equation. The next we are trying to solve parabolic PD. Parabolic PDs. Yes. So that is like a heat equation. Okay, I'll just go through it because we'll continue from this. Okay, in this class. So you know this is a heat equation. This is known as a heat equation. What does the heat equation does? I told you that class. Okay, I told you that take this bar. Take this bar. This is a bar. Okay. What do you do with this bar? You heat it. You heat on both its ends. Here it is 30 degrees Celsius. Here it is 40 degrees Celsius. Yes. So how the heat propagates, from which end the heat propagates to which end? You all know from your physical sciences in your high school or school days that heat flows from higher temperature to lower temperature. Yes. So therefore, you know already that the heat will flow in this direction because it is 30 degrees here and 40 degrees here. Yes. So heat is going to flow in this direction. That means temperature will be smoothly distributed from this point to this point. Okay, maybe here you can get 35, 37, 39, and 20, like 32, something like that. Okay, but it will smoothly distribute. Okay, but how smoothly the heat distributes, how smoothly the heat distributes depends on the physical factors of the metal. Yes, if it is a steel or iron, like it will go very fast. If it is copper, it will go a bit slow. If it is aluminum, it will also go very slow. Okay. If it is silver, it might go fast. So depending on metals. So there is some physical characteristic on how heat can be distributed through the metal. Okay, but anyway, we will not go into that physical depth. We will say that in mathematical, we will say that some constant for each metal is there, and that we denote it by alpha or something. Okay, so the length of the metal also matters. Okay, the length of the metal also matters. So if you hold one beam, if you hold one beam from that end to this end, okay, suppose Durga is holding that metal there and Sriya is holding that metal there, and Sriya is mischievous. So what he will do? He will he will heat the metal to 500 degrees Celsius so that Durga will get that thing. Okay, so he will do that. So, but the metal is so long that Durga is also cunning. She will know that it is red hot there. So she will leave. Why? Because by that time the heat would not have transferred. Yes, because the length is very long. The length is very long. If the length is short, then heat gets closer. One example is like how many of you are using matchbox or matchsticks? How many are using mastics? Mastics. Mastics, yeah. Rohit RB is using mastics. Okay, good. Good, he accepted. Okay. Okay. So the mastic, how it looks? The mastics looks like this. Yeah. Okay, this is the mastic. Okay. I think red. Yeah. So this is the mastic. Okay. What you do? You light it up. You light it up. Yes. So it lights up. Then what happens? Within few seconds, your finger is here. Okay. Your finger is here. Huh? So your finger will catch the fire. Yes. So then within that time, if you don't do, your finger will catch the fire. Why? Why it happens within a short fraction of time? Because the length is small. The length is tiny. Yes. If the matchstick was this big, then you keep on lighting many things. Okay. It will still go on. So length matters. Length matters. So length. So therefore we are worried about the length. What is your length? L. Okay. So now I hope you can understand why these parameters are being considered in this case. Okay. So what is the length of this metal? Like this is my domain. This is my domain. In mathematical sense, you can say this is a domain. Okay, where the heat flows. Okay, it doesn't matter what is the heat here. Does it matter? What is the heat here? Here. Does it matter what is the heat here? No. Heat only matters in this beam. Only inside this beam of length L. So therefore, after length L, it doesn't matter what happens. Yes, it doesn't matter. So therefore, from 0 to L, X will varies from 0 to L. T is the temperature and small t is the time. Okay. So temperature varies for both the distance and over the time. Yes. Take any point of the metal here at any position. Suppose the temperature is 30 degree now at time t equal to 0. Do you think that the temperature will be the same 30 degree at t equal to 2 seconds? No, it will at least decrease by 1 2 degrees, 28, 27 something. And so at that position, it is also changing with time. So temperature changes with respect to position and also changes with respect to time. So therefore, it makes sense to write t as a function of x and small t. I hope that is intuitive now. That is intuitive. Okay. Our job is to find this. Our job is to find what is the temperature at which location of the beam and at what time period. That is our job. That is our job. How we can do that? How we can do that? Okay. So we can do it like this. You take some initial condition like t equal to 0. You can see. You can divide this length L into how many pieces up to you. Okay. You can say it is x1, x2 up to xn minus 1 from 0 to L. You can divide it. Okay. And these are the temperatures at t equal to 0. Then t equal to 1, you apply the numerical method. For that t equal to 1, you solve it. Then go to the next layer. For t equal to 2, you solve it. Then go to next layer, next layer. What time you need the temperature, you can do it. Up to what iteration you need. Okay. I hope that is clear. So how to solve this partial differential equation? So we don't need actually I think many of your bachelor students who have studied PDE in their bachelors might have derived an actual solution for this. There is an analytical solution for this equation. Already a big proof is there, but we'll not see that in this course because that is not the aim of this course. Our aim is to what is our aim? Our aim is to find the temperatures at different locations of the beam at different time periods using numerical methods. Okay, so therefore, in numerical methods, only iteration is there, minor algebraic calculation is there, dealing with numbers. That is it. Okay, fine. So, if you get a PDE or ODE, the first thing we do in numerical methods is to discretize it. Okay, so discretization. So this is another method known as FTCS. Forward. We are marching forward in time. Central scheme method. Okay, forward time central scheme. Forward time central scheme. Okay, fine. So how we will do it? Dou capital T by dou small t can be represented as Tin plus 1 minus Tin by delta T. Okay, it is just like a slope form, y2 minus y1 by x2 minus x1. That kind you can think of. Okay. Dou 2 t by dou x2. We wrote it previously in the class. Okay. Ti minus 1 n minus 2 ti n plus ti plus 1 n. Okay, divided by delta x square. Okay. Now what you do, you just equate them together. You equate them together. So what you will get? What you will get? So when you equated them together, last class we did this. You can see tin plus 1, which we need, which we want to find, can be written as tin, the past value. Okay, the past value plus this is the physical constant. This is the physical constant. Alpha is a physical constant. Delta t is how much grid size you want to make in time step. Delta x is the grid size what you want to make in the beam step. In the beam, what small difference you want to find. Okay. And then there is this term. Okay. So we will solve this now. We will solve this using an example. Okay. And we saw that if you choose delta x to be say 0.02, the solution will converge. It has been seen experimentally. But when you take delta x to equal to 0.01, the solution diverges, which is very unintuitive. Yes, not intuitive. Everyone thinks that if you take 0.02 converges, then 0.01 also you take, it should converge. But doesn't happen. Doesn't happen. This was observed by Nicholson. Okay. And then he came to know that this forward time central scheme is not unconditionally stable. That means whatever step size you take, it is not guaranteed that the solution will always converge. There are some conditions where the solution will converge. There are some conditions where the solution will not converge. Okay, we will derive it today. We will derive it today. Okay. So this method, FTCS, is conditionally stable. This method is conditionally stable. Okay. So it depending on a particular condition, the scheme is stable. That means it will work. Okay. So therefore, Nicholson thought that this scheme is not always stable. So this scheme is not good. This scheme is not always stable. Depending on a condition only, it is stable. Okay. That condition we will derive. Okay, you will see. So without holding that condition, the scheme is not stable. Like it won't converge to the solution. So what can we do? Can we make a scheme to solve this heat equation to make the scheme unconditionally stable? To make the scheme unconditionally stable, that means whatever initial condition, whatever step size in delta x, delta t you take, always the solution will converge to the actual solution. Okay. So that is developed by Crank Nicolson. So that method we will be learning today. Crank Nicolson method. So that is the central method in PD is actually numerical methods. Okay. So yes, forget about this. Okay. Let us start with this problem. Okay, let us start with this problem. This is a heat equation problem. So you can see that at time t equal to 0, okay, the from x equal to 0, from x equal to 0 to x equal to 1, all the values are being given to you. Yes, from 0, 0 0.3, 0 0.6, 0 0.9, 1.20. Okay, this is the first time t equal to 0, the heat the data is being given to you, the temperature data is being given to you. Your job would be to find what are these values. It is not zeros. You have to find these values. You have to find these values. Yeah, these values are also being given to you. Yes, the boundary values are given to you. You have to find basically wherever you are seeing zeros. I mean, here. I mean, you have to find you have to find this entire thing. Yeah. How we can find this? Using this FTCS, can you find this? You have to use FTCS, this formula here, tin plus 1 equals to this. Using this formula, you have to find the solutions. Yes, this is the class 1. You start. Yeah. So these values are given to you. Okay, like these values are being given to you. The yellow things you see are being given to you. You have to find these green things. Ignore the left one, but yes, you have to find the green things. That is unknown. So you have to use the forward time central scheme to solve this. You know that based on the past value, you can compute the future one. So you can find it. Okay. So yes, you tell me what are these values. But yes, so wow, yeah, I think you can do it. All the data is in this figure. All the data is in this figure. Can't see. Yeah, let us solve. Okay. Check that tin plus 1, ti at that location, ith location and next time step depends on what values. Depends on what values. Tin plus 1, suppose you want to find this value, suppose in red. That value is in the left. That depends on tin. Tin means the down value. Yes, tin means just the below value. That is there, plus some constant is there, ti minus 1 n. I minus 1 means the left hand side. Left hand side means this value. Yes. Minus 2 tin. That means the same value. Yes. Then ti plus 1 n. That means this value. I plus 1 is the right hand side. So if you want to find this unknown, it depends on this. Yes. Got the idea? Similarly, if you want to find this value, it should depend on this value, this value, this value. Yes. Got the idea? So it is like this. If you want to find this value, it depends on the below value, the left value, the right value, based on this formula. And yes, alpha you can take one. Alpha you can take one. Okay. So the idea is simple. Now you know how to solve the heat equation. Okay, over the time period. So here it is varying with respect to x, and here it is varying with respect to t. Okay, so you are computing the variation of the temperature in both space x and time t. Okay, and you are generating the solutions without going across any hard analytical methods for PDE. Just by doing plus minus multiplications and playing with numbers, you are generating the solutions and analyzing the variation of temperature with respect to the space and with respect to the time. Okay, fine. So now, as I told you that this FTCS scheme, forward time central scheme, this scheme, okay, is conditionally stable. That means for some step size it is stable, for some step size it is not stable. Now under what condition it is stable and what condition it is not stable, that we want to know. Okay, that we have to derive. So this is the derivative part where I want to show you that it is conditionally stable. That means in what condition it is stable and what condition it is not stable. Okay, so let us do it. So as usual, let us write our uh, temperature form, that the equation dou T by dou small t is equal to alpha. Hmm? Yes, dou to u by, sorry, dou 2 T by dou x2. Yes, this is the heat equation. Yes. Now using FTCA scheme, what we generated T I n plus 1 equal to T I n plus alpha. Hmm. 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 T I minus 1 n. Hmm. Okay. So this is our iterative scheme. This is known as the iterative scheme. This is known as the iterative scheme. This is the iterative scheme. Okay. Now, how to analyze the stability? Okay. So as usual, you know, whatever you are doing here is all approximate. Whatever you are doing by numerical method is always an approximation. Yes. And you compare with analytical solution. Okay. The difference between analytical solution and numerical solution is the error. So if your method is not converging, the error should grow, isn't it? If your numerical method is not converging, the error should grow. Yes. So we want to see when the error doesn't grow. If the error doesn't grow, then the method is stable and we want to find when it is stable. Simple. Okay, the simple logic. So suppose, let us call this quantity as R. Okay, so that we don't have to write again and again alpha delta t by delta x square. So we'll just write it as R. Suppose solution D, the solution D represents the infinite precision machine. Okay, that means it is an analytical solution. It is an analytical solution. That is the D solution. Okay. And solution N represents the finite precision machine. That is finite precision machine. That means this is via numerical methods. So this is via numerical methods. This is analytical. This is analytical. Okay. So our job is to what is the error? What should be the error? So the error is equal to error is yes. Yes, we can write it as n minus d. Okay, just the difference. It is just the difference. Okay, so yes, so how can we compute this? Any ideas? How we can actually start the idea? Like how can, okay, you got this idea that error is n minus d, but how we can, after that, what to do? Think. After that, what we should do? Any ideas? Any ideas? Hmm? What to do? Okay, I will tell you. I told you it is a solution D. I told you it is a solution. I told you it is a solution, right? So what we should do, if it is a solution, if it is a solution D, then it should satisfy your equation 1. If it is a solution, it should satisfy the equation, right? Isn't it? How many of you agree? If it is a solution, it should satisfy, right? So therefore it is good, it is true to write this, isn't it? Agree? I hope it is correct. Now, n is also a solution, right? N is also a solution. N is also a solution. So what we should write? N is also a solution. So n plus 1 is also equal to n plus R, then n. Agree? Agree? So what we should do now? To find the error, why we did this? To separate each other, to find the error. So you just subtract these two equations. Subtracting these two equations, what you will get? N minus d epsilon. Epsilon is the error. Epsilon I n plus 1 is equal to epsilon I n plus r epsilon I minus 1 n minus. Agree? Yes. Agree, no? Okay. Now it is very interesting. Now this is very interesting. The interesting thing is, see this yellow one. See this yellow one and compare it with equation 1. Compare it with equation 1. What do you think? The error also satisfies that equation. Error also satisfies the heat equation, the iterative scheme. So error is also a solution. So error is also a solution because error is satisfying the equations. Yes. So yeah, what to do? This is a good observation, right? Because instead of t, you just put epsilon, the error, and it is following. Exactly, it is following the equations. So what we should do now? Any ideas? I'm asking you to think what we should do next. You see how step by step we are exploring new things. Through every step where I'm training you to think, and also at the same time, we are exploring the next step. Okay. Now what you got? What is this yellow thing is so important? Why the yellow shaded yellow is so important? Why? It tells you how error grows. This tells you how error grows with I and n, isn't it? Epsilon I n plus 1. What is the next error? What is the error at the next step is being given by the right hand side. Yes. So in order to know, so when the error, when the system will not be stable, if the error grows, yes, if the error grows, the system is not stable, right? When the error grows, error will grow when epsilon I n plus 1, error in n plus 1th time step is greater than error in the nth time step. Agree? Agree? So therefore, it is the ratio that is important to us. It is the ratio of the error in the future and in the past that is important to us. So that is something important and it is known as the amplification factor. Yes. So G is the amplification factor. Like how the error has amplified, how much the error has amplified. This is given by EI n plus 1 divided by epsilon I n. The error in the n plus 1th time step divided by error in the nth time step. Can you say what is the value? 1 plus 1 plus r epsilon I minus 1 n. Agree? So for the solution to be stable, for the solution to be stable, for the solution to be stable, what we need? We need mod G, like the error, the amplification factor should be, yes, less than equal to 1. Less than equal to 1. Error can stay constant also. Error can stay constant. That is when magnification factor will be equal to 1. And in future time steps, your error should decrease, not increase. But can you tell me what happens here? How, yeah, we got this 1 plus r something. How we can proceed from here? How we can proceed from here? Any ideas? No? This is exactly where it is your assignment. Okay. Exactly, this is the place where your assignment begins. What we should do next? Okay. What is next? So you have taken my notes already. Okay. It is there in the notes. So but it is incomplete in the notes. If you just copy it, paste from the notes, then I will know. So you have to write it. Okay. Those who just copy paste from the notes, it is wrong because it just jumps from Kerala to Bangalore. Okay. The step jumps from Kerala to Bangalore. Okay. So you have to write stepwise. Anyway, so I will tell you the extract of this, but this part after this you have to solve it for the assignment next class. Okay, this is assignment one. Assignment one. Okay, fine. So G, the amplification factor will turn out to be something like 1 minus 4R sine square beta by 2. Okay, where beta is equal to something like, I think, Km delta x. Where Km comes from and all, that you should think. That is in my notes. Okay, but just that is in my notes. You will get the pictures. But just know that if you solve it, if you solve this equation, you will arrive into this form. Okay, it is very surprising, but you will arrive in this form. So G, the amplification factor is 1 minus 4R sine square beta by 2. Okay. Now the idea is, can we plot this guy? Can we plot this? Can we plot this? Can we plot this? Can you use Desmos? Can you see this in Desmos? So open Desmos and just plot this function. So actually we need mod G to be less than equal to 1. Okay. So that means G should be in between -1 and 1. Yes. So -1 less than equal to G is this guy. 1 minus 4R sine square beta by 2, right? This should be in between -1 and 1. Agree? Now what it tells us. So observe that this case, that is 1 minus 4R sine square beta by 2 is less than 1 is always true. Because R is always positive. Sine square beta by 2 is always positive. You are subtracting from 1 a positive quantity, which is always less than equal to 1. So this is always satisfied. This is always satisfied. Okay. But this is the tricky part. This is the tricky part. Okay. Why? Can we solve this to find the condition? So what you can do, take this on the right hand side, 4R sine square beta by 2 is less than equal to 2. So what you get? R is less than equal to 2 by 4R sine square beta by 2. Yes. So that is, you are getting 1 by, sorry, this R is not there. 1 by 2 sine square beta by 2. Yes. So what do you think? Sine square beta by 2. So you want to find what is the maximum error. What is the maximum error? What is the maximum you can do? So you can take sine square beta by 2 equal to 1. You can take sine square beta by 2 equal to 1. Okay. Fine. You can take sine square beta by 2 equal to 1. And then you will arrive at R is less than equal to 1 by 2. R is less than equal to 1 by 2. Yes. So what is R basically? We have taken R, right? R is, you remember, alpha delta t by delta x squared, right? Is less than 1 by 2, right? So this is the condition. This is if the condition here, this condition is satisfied, your method will be stable. Else your method is not stable. Okay. So therefore, it depends. Now you can see that your method depends on alpha, which is constant already. So your method depends. So you should choose in your FTCS scheme, forward time central scheme. Okay. You have to choose delta t, delta x such that choose delta x, delta t such that this is satisfied. This is satisfied. If it doesn't satisfy, you will never get it. Okay. Your solution will never converge. So this tells us, this yellow shaded equation tells us why you cannot always reduce delta x and also cannot reduce delta t and expect stable and accurate solutions all the time. Okay. The more delta x you make it more small, if you make delta x more small, it is in the denominator. What will happen? 1 by small quantity is big. Then there are chances that you will cross 1 by 2 and your method won't be stable. You understood the fact? You understood this idea? Yes. If you make delta x very small, then 1 by delta x squared is getting very big. And there are chances that it will cross 1 by 2. Okay. Because alpha is small. Alpha is constant. Yes. So you have the control over delta x and delta t. You have to change it in such a way that you should be in between 0 to 1 by 2. You should not go between that, be above that. If it is above that, your scheme is unstable. Okay. This is very important. Okay. You might expect. Anyway. So, yeah. So, how many of you have plotted this? How many of you have plotted G? How many of you have plotted G versus beta? How it looks? Any ideas? Many of you you must have used Desmos, no? Did you check with Desmos how it looks? 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 Do? And also, like, I think uh, our this is third test, right? The fourth test will be lab test. Okay. Hmm. So, yeah. So how this amplification factor looks? How amplification factor looks like? Yeah. So it will look like this. So for put r equal to 0, put r equal to 0. If you put r equal to 0, then g is just 1. G is just 1. G is just 1. Yes. Isn't it? You'll just get one line. Fine. If r equal to 0.2, if r equal to 0.2, you will get something like a bell shape. Yes. So this is for r equal to 0.2. Of course, it will be infinitely oscillating, but you have to take a small chunk of it. Okay. G that beta axis cannot be negative. So you look only in the positive part and only a chunk. It represents one oscillation like this. So the more, if you increase the value of r from 0.2, 0.3, 0.7 like this, the more you increase r, the bell goes on increasing. Okay. The bell increases. So this is for say r equal to 0.7. The moment, so this is say r equal to 0.5. So this guy, as you know, this is r less than equal to 1 by 2 is marginally stable. So this is equal to, so this is marginally stable. Okay, fine. And r equal to 0.7, r equal to 0.7. What will happen to it? Is it stable? So the more you increase r, it depends. Yes, it goes down. Yes. So for r equal to 0.7, is it stable? Okay. So I hope you can understand that why this scheme is conditionally stable. So this tells you why why the FTCS scheme is conditionally stable. Okay. It tells you why. Okay. Because R should be less than equal to 1 by 2 for, for the FTCS scheme to be stable. Okay. So this is unstable. R equal to 0.7 is okay. Fine. So let us look into something more, that is, as I told you, Nicholson found that the scheme is not stable. okay, under certain conditions. Therefore, he thought like, can we find a scheme which can be stable all the time, unconditionally stable? What does unconditional unconditionally stable? Okay, so do you know about what is meant by unconditional stable? Yes, anyone? Implicit FTCS schemes. Okay, the FTCS scheme only we will play with. Okay, so it is important to understand the Crank Nicolson method actually. Anyway, so this is known as the implicit FTCS scheme. Okay, so here, rather than, what was your FTCS scheme before? Can you tell me? Ti n plus 1 equal to Tin plus alpha delta t by delta x squared. Yes, times Ti minus 1 n minus plus, sorry, Ti plus 1 n. Yes. So this was your implicit scheme. Sorry, this was your FTCS scheme. Okay. Now people thought that, why can't we change this scheme a bit? This is the road towards making Crank Nicolson method. This is a road towards making. So what you do, you improve your version, you improve your code, version 2.0. This is version 2.0. This is known as the implicit FTCS scheme. That means it tells you that the heat equation you have, that is dou T by dou T equals to alpha dou 2T by dou x square, right? This you discretize in a different way. This you discretize in an implicit way. What is the implicit way? Implicit way means the unknown will be in your equation. That is implicit. The unknowns will be in your equation. That is implicit. So this is how we discretize it. Ti n plus 1 minus, yes, Tin divided by delta t equals to alpha times, yeah, this part will be changed. This part we will have to change. So can you look into your notes and tell me how shall we change it for implicit method? Just check your notes. So I hope uh, you have written something like this: Ti minus 1 minus 2Ti plus Ti plus 1, no, divided by delta x squared, right? But here, here everywhere it was n. Here everywhere it was in the nth step. But in implicit scheme, it will be all n plus 1. Yes, this is the implicit scheme. Okay, because to do this, you have to know the value at n plus 1th step. Yes, this is the implicit FTCS scheme. So this is implicit FTCS scheme. Okay, fine. So can we, so there, of course, there is some error, order of delta t, delta x squared, that is there. In numerical method, always the error term is there. Okay, but can you do some calculation based on it? So what we can do, you can write it Tin plus 1 minus Tin is equal to alpha delta t by delta x square will be there. So that we have taken it as a R. Yes, R times Ti minus 1 n plus 1 minus 2 Ti n plus 1. Yes. Now observe, can you see something common on either side? Yes, this guy is common with this guy. Exactly, you can bring it to there. So what you get, 1 plus 2R. 1 plus 2R Ti n plus 1, no? Minus Tin, okay, equals to R times this. Is it correct? Did I do correctly? So this we can write in a better way, that is R times Ti minus 1 n plus 1 minus 1 plus 2R Ti n plus 1 plus R Ti plus 1 n plus 1 equals to minus Ti of n. Okay. This is the only guy who you know. This is the only guy who you know. Known. This is the known quantity. This is the known quantity. Yes. This is the known quantity. Others are unknown. Others are, these all are unknown to you. These all things are unknown to you. Sorry. These are unknown to you. Okay. These are unknowns. Fine. Can you see what is going to happen? Can you see what is going to happen? So if you put that in your grid, you will get a very nice structure. You will get a very nice structure that is of a tri-diagonal matrix. Tri-diagonal matrix you will get. Tri-diagonal matrix with these coefficients. Tri-diagonal matrix with these coefficients will. Okay. Of course, we will not solve it, but this is just the road to Crank Nicolson, so I had to say it. Okay, now what Nicolson and Crank and Nicolson, two scientists, they thought is, how about we take 50% of the implicit scheme and 50% of the explicit scheme and make a new method that is Crank Nicolson. And surprisingly, it worked. Okay, it seems very odd. It seems very odd, but technically you can think it like this: like, can we use P% of explicit and Q% of implicit? Okay, so where P plus Q equal to 1. Okay, you are understanding. It is just like adding sugar to your lemon water. It is just like adding sugar to your lemon water. Okay, so what you do? So what you do basically, you add lemon water 1 liter. Okay, for some people, if you add 10 gram of sugar, it is okay. For some people, if you add 30 gram of sugar, it is not okay. They need to add 50, 100 grams of sugar. Okay, they need sugary drink. Okay, so it depends. So you add 500 ml of water, 20 grams of sugar, then 600 ml of water, 30 grams of sugar. So you make a combination of it. So the same combination Crank Nicolson thought. Okay, so I have explicit method, which you know already know. I have implicit method. How about I combine them together? Okay, how about I combine them together to make Crank Nicolson method? So you can see that you can take P equal to 1 by 3, Q equal to 2 by 3 also. P equal to 1 by 4, Q equal to 3 by 4 also. Yes. There are infinitely many methods you can generate from this, but researchers, they finally came to a conclusion that if you take P equal to 1 by 2 and Q equal to 1 by 2, it is the most accurate one. Out of all this, it is the most accurate one. Okay, it is the most accurate. Fine. Okay, so this P equal to 1 by 2 and Q equal to 1 by 2 is referred to as Crank Nicolson method. Is referred to as Crank Nicolson method. Okay. Yes. So it is known as the Crank Nicolson method. So let us write that. So this is the combined method. That is, this is only in the discretization. That is Crank Nicolson. So yeah. So this motivates me towards Crank Nicolson method. This is Crank Nicolson. Okay. So what is the heat equation? Dou T by dou T is equals to, yeah, dou 2T by dou X2. Fine. Okay. Fully done. This is the heat equation. So how we are going to discretize it? Any ideas? As I told you, TIN plus 1 minus TIN by delta T, right, is equals to alpha times what? Yes, exactly. Here you have to take 1 by 2 of both methods. Alpha times something. What is that something? Half of implicit plus half of explicit. Yes, so that is what I am going to write here. So Ti n plus 1 minus tin by delta t is equal to alpha by 2. Okay, that 2 I can take it out as common. Alpha by 2 times, can you say, tell me the method for explicit? The first one you learned? Ti? Hmm? Plus, what is the implicit scheme? Ti minus 1 n plus 1 plus, sorry, minus 2 ti n plus 1 plus ti plus 1 n plus 1 divided by delta x squared. Yes, this is Crank Nicolson. Okay, so it looks very complicated, but yes, it gives you the most accurate solution you could have done so far here. Okay, but you can write it in very simple way, like as a tridiagonal matrix. Okay, as a tridiagonal matrix. Okay, so finally this equation, when you boil it down, you can just write it, convert it to a tridiagonal matrix and solve it. Okay. So finally, let me know that you will get this solution. Finally, you will come to this solution. Can you try this? R by 2, alpha delta t by delta x square I have taken as R. Okay. So R by 2 times ti minus 1 n plus 1 minus 1 minus R ti n plus 1 plus R by 2 ti plus 1 n plus 1. Okay. Equal to minus R by 2 ti minus 1 n minus 1 minus R. Yes. Yes. So again, you will have this, you can represent as a tridiagonal matrix. Tridiagonal matrix. Can you check? Can you check that from this you are getting the blue one? Just you have to try this. So that you will get a feel that you are actually getting a tridiagonal matrix. Okay. So why I am telling you a tridiagonal? Because ith, you see, I is in this direction. I equal to 0, 1, 2, 3, 4 is in x direction. N equal to 0, 1, 2, 3 are the levels you worked, right? N is the time. N is the time. Yes. So when you put all this coefficient R by 2, 1 minus R in respective places, that will turn, that is a matrix. Before some time, I gave you a matrix, no? That finding the temperature at each point in 0, that is a matrix. So if you put these values, it will be like a tridiagonal matrix. What is a tridiagonal matrix? It will have diagonal elements. It will have one above the diagonal. It will have one below the diagonal. All other things will be 0. This is a tridiagonal matrix. So wherever you go, you will always face tridiagonal matrix. Whenever you want to solve anything, and tridiagonal matrix will come everywhere, even in deep learning. Tridiagonal matrix always comes. Okay, because you will always, because diagonal matrices are very popular. Okay, and when your method becomes a bit more complicated, it gets complicated by +1 and -1. That means you will have some terms above the diagonal, below the diagonal. So tridiagonal matrix always comes. So in most important methods, tridiagonal matrix always comes. Most important, like Crank Nicolson. See, you never got this method in explicit scheme, but you saw this in implicit and explicit 50-50, Crank Nicolson. Okay. So somehow they just appear. Okay. So, okay, fine. This is a bit hard method. Okay, we got it. But this Crank Nicolson scheme is how it is unconditionally stable. That we have to check. How Crank Nicolson scheme is unconditionally stable. For this method also, similarly, you can compute epsilon I. That is epsilon I is equal to Ni minus Di. Yes. And same way you can, that can lead you to amplification factor. That is epsilon I plus 1 by epsilon I. We will not do that calculation again. Okay, that is very hard now. Okay, but you can do it. You can arrive, you can in books it is there that you can arrive in this form: 1 plus 2r minus 2r cos beta. Same, beta is some quantity you have to show in your assignments. Okay. So this quantity, can you plot it? Can you plot it? Can you plot this quantity for different values of R in Desmos? Can you plot this for different values of R, G, beta, for different values of R, like R equal to 0.1, R equal to 0.5, R equal to 0.7, 1.2, whatever. You will see that in all these cases, whatever you do, in all these cases, G is always less than equal to 1, always, for all R, for all R values. So that means whatever R, you know, R is alpha delta T by delta X squared. For any value of R, this method is giving you amplification factor less than 1. What does it mean? For any step size delta X, delta T you choose, this method will reduce the error. Yes, the error will never grow. That means the method is unconditionally stable. Unconditionally. That means whatever delta T, delta X you choose, it doesn't matter. Mod G is always less than equal to 1. Always. But this you never got in your FTCS scheme. FTCS scheme, see the difference. In FTCS scheme, you need R to be less than equal to 1 by 2 for stability. This is the condition. But this here, this guy tells you that Crank Nicolson method is unconditionally stable. Okay, is unconditionally stable. And it is second order method also. But anyway, yes. So I think, yeah, we can just solve one problem on Crank Nicolson and then we can stop it. So yeah, we'll solve one method for Crank Nicolson. Yeah. Fine. So keep, I hope you have written all the things for Crank Nicolson. Else we have to juggle between 2 pages. Else you have to juggle between 2 pages if you have. Anyway. So this is the question. Solve the method, solve by Crank Nicolson. Okay, solve the heat equation by Crank Nicolson method. Where delta X, the step size is given to you as 1 by 4. Delta T, you can take 1 by 8. You take delta T is equal to 1 by 8. Here in class, you will solve. At home, assignment 2 by taking 1 by 16. Assignment 2. Okay. By taking delta T to be 1 by 16 at home, you will resolve this and check whether it is getting accurate. Okay. And given that dou u by dou T is equal to dou 2u by dou x2, this is the heat equation. X is lying in between 0 to 1, time is greater than 0, of course. Given that u0t is equal to u1 comma t, that is at x equal to 0 and at x equal to 1, for every time you have the temperature to be 0. Okay. And u x at time t equal to 0 at any point x is 3 times x. Okay. This is for time t equal to 0. Of course, ux comma t. So you can see it as ux comma t, the solution. Can you solve it by Crank Nicolson method? So I will solve some part of it. I will solve some part of it and then I will give it to you. So here alpha is what? Alpha is 1. Yes. So therefore, what value you have? R is alpha delta t by delta x squared, no? So this is 1 times delta t is, what is delta t? 1 by 8 divided by delta x squared is 1 by 16. So this value should be, this is equal to 2. So R is equal to 2. Can you use explicit FTCS? Can you use explicit FTCS scheme to solve it? Can you use a explicit FTCS to solve this method? Why? Yes. Harilal is right. So mod R is Sri Haris. Yeah. So mod R is greater than 1 by 2. So therefore it is unstable. Okay. So you cannot use FTCS scheme. So you can expect questions like this. You can expect question like this. If you are given a question, you can be asked, can you use this method? Yes or no. Why no? Okay. Point wise questions can be there. So be prepared. So this is the idea. So can you tell me the Crank Nicolson scheme? What is the Crank Nicolson scheme? What is the Crank Nicolson scheme says? Yes, tell me. Tell me the scheme. Okay. So tell me the Crank Nicolson scheme. Else how we will proceed? Hmm? R by, I will give you. Can you note it down? Can you note it down and tell me? Can you note this down and tell me again? You have written down, no? You have written down. Okay, so then we'll no need. Yeah. Yeah, tell. Yeah. Yes, R by 2. Hmm? R by 2. Huh. R is alpha delta t by delta x squared. I wrote in R only, no? Tell. What is the scheme? Yeah, tell. R by 2 equal to plus minus 1 minus R. Huh. Hmm. Yes. So can we use this? Can we use this? So put R equal to 2. Let's see what you get. Ui minus 1 n plus 1. Okay. Minus of minus 1. That is plus, no? You should check if I am doing everything correct. Okay. Sorry. Plus ui plus 1 n plus 1, no? Equal to minus ui minus 1 n minus uin. Yes. Is it correct? Is it correct? Is it correct? Okay. So are we not getting anywhere 3? We are not getting 3. Any terms can be added? Can we add any terms? No. Let me check it again. It's correct, right? How many of you think it is correct? Is it correct? It's correct. Correct. Then solve. You can solve. Yeah. So you already know the initial values. Can you solve it? But before that, I just want, because you will start doing the computation, I think something might be wrong here. Can you check it again? Is anything wrong here? Yes. Where? Where? Where plus? Here. Here. Where mistake is there? This one. This one. Okay. Is it correct? Plus 1 minus r tin. Other places it is okay? Hmm? Okay. You can start doing the computation. Hmm? Can you start? Iterative scheme is being given to you. So what you have to do, just put the values and start. So what we will get? We will get something like this in terms of u. Minus r times u I minus 1 n plus 1, 2 plus 2r times u I n plus 1 minus r times u I plus 1 n plus 1 is equal to, can you check this carefully? You check whatever I'm writing is correct. Is it correct? Correct, no? Okay, fine. So if you put r equal to 2, this equation boils down to this form, minus u I minus 1. Is it correct? If you substitute, Adil, it is correct. Can you go from this step to this step by putting r equal to 2? If you put r equal to 2, can you go from that step to this step? And you know already that u00, that is I equal to 0, n equal to 0 time step is equal to 0. u10 is equal to 0.75. u20 is equal to 1.5. u30 is 2.25. How you will get all this? From where we got all this? Yes, 3x. And boundary values are already given to you, u0, 1. That is u0 time step 1 is 0, u fourth, the time step 1 is 0. Take advantage of this 3x. From that, you can generate all this data. Can you check it? Is it correct? So basically, we have this like basically we have this at I equal to 0, x equal to 0, I equal to 1, x equal to 1 by 4, equal to 2, x equal to 1 by 2, I equal to 3, x equal to 3 by 4, and this is I equal to 4, x equal to 1. And this is at time t equal to 0, that is j equal to 0, t equal to 0. These are given to you. What is your aim? Your aim is to compute at the next time step, that is j equal to 1, t equal to 1 by 8th. Time step is given, delta t is 1 by 8th is given to you. Your assignment is to solve by taking this delta t to be 1 by 16th. Yes. So what you will do, you will get similar points here. You will get similar points here, right? Yes. So this guy is u01 time step 1. This is u11, u21, u3, u11, u21, u31, u11, u01, u11, u21, u31, u41. Yes. Your job is to find this from here. Okay. So check what is being given to you. Don't worry that these are heavy equation, what I do know. Just think what is being given to you, what you don't know, use the iterative scheme, get the answer. Finish. If you just look and don't do, you will not get it. Use your pen. Use your pen and this. You want paper? Finished paper? Okay. So what you will get? Is it correct? Are you understanding? Understanding. What? How many of you are understanding? I equal to 0. UIN is there, no? UIN term is there. If you put I equal to 0, N equal to 0, what you get? U00. Put something. Put your heart into this a bit. This is the last method.